Hi everyone, my name is Sydney Katz, and I will be talking about some joint work with Anthony Corso and Chris Strong under the direction of our advisor, Professor Michael Kokendorfer, on verifying image-based neural network controllers using generative models. Neural networks can process image inputs remarkably well, and they're often used in the control of autonomous systems to extract information from camera-based perception systems. To show how these controllers work, we use a running example of an autonomous aircraft taxi system, in which we assume that a camera mounted on the wing of an aircraft takes photos of the runway like the one shown here. The images are converted to grayscale and downsampled to highlight the runway markings, and then fed into an image-based neural network controller, which outputs a control action. The aircraft takes the action, and the system evolves over time according to a dynamics function, which closes the loop. Our goal is then to verify safety properties of a neural network controller with image inputs such as the one shown here. In the autonomous aircraft taxi problem, we assume we have an aircraft situated somewhere on the runway and that we've been given a neural network that was pre-trained to guide the aircraft along the center of the runway. One safety question we could ask here is, will the neural network controller ever guide the aircraft to leave the runway, which could be dangerous? Another question that we could ask is, not only will the aircraft stay on the runway, but will it be guided towards the center of the runway? One way that we could answer these questions could be to simulate the controller from various starting points on the runway and check whether the resulting trajectories satisfy the safety properties. In this case, it looks like they do. However, this approach only samples a finite number of trajectories and could miss out on potential dangerous behavior of the system. What we would rather have is a way to produce a formal guarantee on the system that considers the infinite spectrum of possible trajectories, which is the focus of this work. It turns out that this type of formal verification is actually possible for neural network controllers if we have access to the true state of the aircraft. In this problem, we model the state with the cross-track error, which is the distance to the center line, and the heading error, which is the angle between the aircraft's velocity and the center line. So a state-based neural network controller would take in these two inputs and output a control action, which in this case is a steering angle. And it turns out that using state-of-the-art techniques in neural network verification, we can actually verify the closed-loop performance of a controller set up like this one. I will talk briefly about how this state-based closed-loop verification works, since it's important to understand before we transition to image-based verification. The way that it works is that it takes the space of inputs we care about, in this case heading errors between minus 30 and 38 degrees, and cross-track errors between minus 10 and 10 meters, and partitions the space into a finite number of cells. Then, for each cell, we can run the range of states that it represents and the neural network controller through a neural network verification tool. I won't get into the nitty-gritty about how these tools work, but they essentially rely on various mathematical techniques to reason about the possible outputs of a network given a continuous range of possible inputs. In this case, we can use them to determine the minimum and maximum control output among all states in the cell. Using this result, in conjunction with the dynamics model of the system, we can determine an over-approximated set of states reachable at the next time step. We then look at the cells that this new region overlaps with and repeat the process. We can run this reachability analysis in multiple directions, each giving us different information. If we run it in the forward direction, we can answer the question about whether the neural network controller will keep the aircraft near the center of the runway. In this case, we start with a reasonable set of initial conditions in which the aircraft starts on the runway and with a heading error magnitude of less than 10 degrees. And then we progress the reachability forward until we converge to an invariant set, which represents an over-approximation of the states we will eventually reach with our neural network controller. The final set in this case contains states near the center of the runway with low heading error. To answer our second question, we can run the reachability in the backwards direction. In other words, we can start in dangerous states, such as states outside the runway bounds, and work backwards to see which states the dangerous states can be reached from. This results in an output such as this one, where gray cells represent states where the aircraft will never leave the runway, and red cells show states where the aircraft could potentially leave the runway. This gives us a state set in which to operate. Before trying to adapt these tools to image-based controllers, we tried to break down what makes these techniques possible for state-based controllers, and we arrived at two criteria. The first is that the inputs to these networks tend to be low-dimensional. For example, in the taxi problem, the state is two-dimensional, and we can even visualize it. Because the number of cells required for the state-based verification technique scales exponentially with the input dimension, this property is a key requirement for these methods to be successful. The second criteria is that the set of plausible inputs to the network is well defined. We know the exact range of cross-track and heading errors we care about, and they make a nice rectangle in the input space. Let's see how these properties hold for an image-based controller, where we replace the true state input with an image observation. Even for this small downsampled image containing 128 total pixels, the input is still 128 dimensional, and our space is no longer low dimensional. Furthermore, our set of plausible inputs is no longer well defined. While we know for a grayscale image all pixels can take on values between 0 and 1, this represents the space of all possible grayscale images. What we actually care about is the subset of images in this space that look like a runway. With the loss of these two properties with image inputs, we cannot directly apply the state-of-the-art tools developed for state-based controllers to image-based controllers. So now we're left asking ourselves how we could overcome this added complexity. And what we came up with was to use a generative model to approximate the set of plausible images. The way this works at a high level is that we train a generative model that maps states and some latent variables to images. We then concatenate the generative model to the control network to obtain a network that maps states and latent variables to control actions. This allows us to bring back these state-of-the-art tools to perform the verification. Finally, because the verification will be with respect to the set of plausible inputs captured by the generative model, it's important that we measure how good our generative model is at doing so. We measure this using a recall metric on the training data. Let's dive into each step, starting with how we train the generative model. In this work, we chose to use a generative adversarial network, or GAN architecture. A GAN consists of two neural networks, a generator network and a discriminator network. The discriminator has access to the training images and is trained to distinguish between real images from the training set and the fake images generated by the generator. The generator takes in a random noise vector and produces an image. It is trained to fool the discriminator into classifying its generated images as real. By training the network simultaneously in a zero-sum game, the generator learns to produce realistic images that mock the training data. This approach has been successful in a variety of applications and typically works best when the generator is a large, deep convolutional network. However, you may recall that our techniques rely on neural network verification tools, which do not play nicely with complex convolutional architectures. In fact, they tend to require small, ReLU-activated multi-layer perceptron networks. Therefore, we need to take an additional step after training to compress the generator network. We do this by using the original generator network as a teacher network, which generates training data for a smaller MLP. Here are some results from applying our training techniques to create a generator network for the taxi images. On the top is a set of true images from the training set, and on the bottom are corresponding generated images. On the right, we show a simulated trajectory with the full resolution image on top, the downsampled image below, and the generated image at the bottom. At least visually, we see fairly good agreement between the true and generated images. When I introduce our recall metric later, I will also provide a quantitative evaluation. With this trained generator, we can begin our verification approach. We assume that we have a control network that takes in an image and outputs a steering angle, providing us with a mapping from images to actions. And we also now have a generator network that takes in a state and some randomly distributed latent variables and outputs an image, providing us with a mapping from states and latent variables to images. Noting that the output of the generator is the same as the input to the control network, we can concatenate these networks to obtain a network that maps from a well-defined set of states and latent variables to actions. With this new mapping, we can now answer the questions we posed at the beginning of the presentation using the state-based techniques we outlined by verifying over all states and latent variables. Here are the results we get from our concatenated generator and control network to answer the question of whether the neural network controller will ever guide the aircraft to leave the runway. We can start with the fully observable case we saw earlier, meaning the controller has access to the true state. As a reminder, the gray area represents states in which, if the aircraft starts in them and follows the policy of the neural network controller, it will never leave the runway. Red states represent states in which it may follow a trajectory that leads the aircraft off the runway. Here are the results when we run the same analysis using the generator and our image-based controller. We still have a fairly large set of safe states. However, the set of unsafe states is larger for the image-based controller. This result could mean that the image-based controller simply isn't as good as the fully observable controller, or that we have more over-approximation error in our analysis of the image-based controller. Answering our second question, we can now look at forward reachability. We see that our image-based controller converges to a slightly larger reachable set than the fully observable state-based controller. However, it still converges to a region near the center of the runway with low heading error. We can also visualize this forward reachability in a different way by overlaying it on the runway, where the blue shaded region shows an over-approximation of where the aircraft could be when starting from a cross-track area between -8 and 8 meters. All of our simulated trajectories that we showed earlier fall within this over-approximated region. The last step we take is to evaluate how strong our guarantee is. The safety guarantees we provide are only as good as our generator network's ability to capture the true set of plausible input images. In order to quantify this, we use a metric called recall, which I will explain using this diagram. There are two sets here. The pink set, P sub G, is the set of all images that could be produced by our generator, and the blue set, P sub R, is the set of all realistic-looking images, or in other words, the set of plausible inputs that we want to verify over. All of the data points are the set of training data images we've gathered, which are assumed to cover the space of plausible inputs. Recall is a measure of how many of our real images can be produced by the generator, shown by the shaded blue dots. Since we want to make sure we verify over as much of the space of plausible inputs as possible, we would want our recall to be as high as possible. However, there's one caveat. Because the images are made up of 128 floating point values for the pixels, we will never identically match a given real image with our generated images. Therefore, what we do instead is to measure the distance between each real image and its closest generated image. If we compute this distance for all of our generated images, we can obtain a histogram that looks like this. A distance of 1 represents 1 pixel difference, but typically spread out over the entire image. By taking the cumulative distribution of this histogram, we obtain a measure of recall as a function of the allowable deviation between real and generated images. We can use this recall metric to compare the performance of generator networks. Here, we ask the question of whether this metric can be used to differentiate a generator that is doing a good job at capturing the set of plausible images from a generator that seems to miss portions of the plausible input space. The top row in this video shows the true full res and downsampled images. The bottom left images are the closest generated images for the best generator we trained, and the bottom right shows the closest images we obtained using a different training procedure that did not seem to work as well. The generator in the bottom right misses large portions of the space of runway images. For instance, it seems to mostly output images from when the aircraft is between dashes on the runway. For more information on the training procedure used for this network, we'll refer you to the paper. We can observe this effect quantitatively using our recall metric. Our best generator is shown in blue, and we can see from the histogram that this generator has most distances below 1. We also see from the figure below that it has a much higher recall than the generator that seems to be missing images. In other words, our recall metric is in agreement with what we observe visually. To summarize, we showed how image inputs dramatically increase the complexity of the closed-loop verification problem, and that by training a generative model, we can convert to a lower dimensional problem. By concatenating the generative model that approximates the space of plausible images to the image-based control network, we can rely on existing state-based verification techniques to verify an image-based controller. Finally, we showed how to use a recall metric to quantify how well the generator network captures a set of plausible inputs in order to assess the strength of our guarantee. This wraps up our presentation. If this presentation piqued your interest, check out the full paper for more details, and of course, don't hesitate to reach out with questions.